Okay, good morning, everybody. Welcome. And let me go ahead and share my screen. Um, let's see, put it on full screen mode. Um, yes, good morning, everybody. Welcome to the webinar. Let's do a quick audio check again. I know we just did it, but I just want to make sure everything is still working. So to our team, can you guys hear me? Can you see me? Yes, sounds good. Yes, yes, yes. Okay, very good. All right. Welcome everybody to this webinar, PMUT Market Trends and Emerging Applications. Um, we are very happy to host this webinar jointly with SilTerra. We have a great program for you. We'll be going for about an hour, maybe slightly over an hour or so. Of course, as you guys probably saw when you signed up, we have 6 speakers for this webinar. So in a way, it's actually a mini conference. So we're very happy to bring this program to you this morning, or afternoon or evening, depending where you're dialing from. We actually have close to 300 participants in this webinar. We're very happy with this turnout. I'll mention a little bit more about that as I make my remarks. So the format will be fairly simple and straightforward. As you guys can see from your screen, we will have the speakers window, usually towards the right of your screen. All speakers will have slides. We'll be bringing them. We'll be bringing up speakers one at a time, and then for Q&A, there is an area, usually it's on the bottom, sometimes it's on the top of your screen. There's a bar, a typical Zoom bar. Everybody should be familiar with that by now. But for Q&A, please use the Q&A area to submit your questions, and we'll take questions after each talk. I will speak a little bit more about the format in my remarks. So let us get rolling, and what I'll do right now is just basically set the stage for the rest of the speakers. I will make a few remarks about the PMUT market, give a few overview, high-level slides just to get us started, and then I'll also speak about the rest of the program for today's webinar. So welcome again. My name is Mike Pinellas, President and CEO of Microtech Ventures. Microtech Ventures, together with SilTerra, are the hosts of this webinar, and we're very happy to host all of you today. All right. Okay, so just a very quick couple of minutes about Microtech Ventures. I think many of you know about us. If you don't, we encourage you to check out our website, microtechventures.com. We also encourage you guys to follow our LinkedIn account, LinkedIn feed and account. We post a lot of interesting articles and content on LinkedIn. So if you go on LinkedIn, you can search for Microtech Ventures, and please feel free to follow us, as well as check out our website. Just as a quick overview, Microtech Ventures, we are a boutique investment bank. Many of you probably know us from before. We are also the publisher of MEMS Journal. That's actually how our business started about 18 years ago. And about 4 years ago or so, we started Microtech Ventures. And Microtech Ventures, again, is a boutique investment bank. We make investments and also provide M&A advisory services for sensors, MEMS, and microtechnology companies. So we're very focused and continue to be focused on sensors and MEMS. And again, if you're looking for investments, please contact us. If you're looking to explore M&A options, whether buy side or sell side, please contact us and we'll be glad to discuss with you. We're making great progress in terms of growing our investment banking practice and M&A practice. And actually, Axial ranked us last year in the top 10 out of 800 boutique investment banks worldwide. So we are definitely getting traction, and we look forward to connecting with all of you at some point sooner or later. I'm sure that we will cross paths because we're very focused on sensors and MEMS. All right. Just also very quickly wanted to mention a few of our conferences that are coming up. These are our next 5 conferences that we'll be hosting. All of them are still online, where our online format, as we've already hosted 3 conferences with our online platform and format. It's been a great success. We're getting very, very positive reviews and testimonials from the participants. People are connecting at our conferences, in some cases even more efficiently than in-person events. And of course, the other big benefit is that you don't have to travel. The speakers don't have to travel, so we're able to get even better speakers than usual because, again, of that the travel barrier is not there. And of course, for people that are participating, they can join us from all over the world. So for the time being, we're sticking with the online format. So you'll see here, we've got cardio wearables coming up in August, automotive LiDAR coming up in September, and we have Microfab Summit in November, medical wearables in December, and MEMS manufacturing in February of next year. Okay, so next I will speak a little bit about the ultrasound sensing modules market, or the ultrasound sensing market overall, I should say. And I'll have a few overview slides. We actually work fairly closely with Yole in some cases, and we're a customer of Yole, and so we've actually asked them to provide us 3 or 4 slides specifically for this presentation that are updated slides and has the latest information. So we actually just got them hot off the presses just a short while ago. So just very quickly here, I'll just give a few highlights. Of course, we saw the COVID impact in 2020 for the ultrasound market, and especially it was felt because the ADAS application is one of the main applications for ultrasound sensing right now. And again, that was impacted by COVID in 2020, of course, unfortunately. The other big existing areas are fingerprint sensors for consumer electronics and industrial automation. So you can see that ADAS is in orange here. Fingerprint sensing is in green, and industrial automation is in darker orange. Everything else is still pretty small, but there's lots of potentials for PMUTs and CMUTs in medical imaging applications, for example, although the volumes are still small. This is another interesting slide, and again, we'll be distributing all of the slides afterwards. So, I will not dwell too much on it, but just a few highlights here. This is again, one of these custom slides that Yole prepared for us. And you can see here how the growth of various applications will go from 2019 to projected numbers in 2025. And that is actually the technologies from which the ultrasound sensors are made. So for instance, you can see here that for automotive right now, automotive ultrasound sensors are made from bulk sensors, piezoelectric ceramics, basically. And you can see that Yole is projecting that they will stay like that for 2025. In other words, the CMUTs and PMUTs will not come in and take that application away from ADAS for park assist. But for automotive and gesture recognition, of course, it doesn't really exist right now, or maybe by now there are some applications on high-end models, but in 2019 it didn't exist. But in 2025, Yole is projecting that this will be a category that's really dominated by PMUTs. I can see that PMUTs are in green, CMUTs are in orange, bulk is in dark orange, and PMUTs are in green. Similarly, if you look at consumer, for example, that's already all PMUT and is going to continue to stay as PMUT. VR headsets, again, PMUTs, and will continue to stay as PMUTs. Consumer user interfaces, some of it is bulk right now. but some of it is PMUT already, and PMUT will take that market share away by 2025. So so what I did here on the right is basically summarize the chart. You can look at it more closely afterwards, but these are the best opportunities for PMUTs, at least as Yole sees them. And of course, nobody's analysis is perfect, but they do a great job with their report. So check it out. And again, the best opportunities for PMUTs, of course, because we're focused on PMUTs in this webinar. Okay, so this is another, a little bit of a busy chart. I will not get into it, but what we did here is we actually took some of our own observations from Microtech Ventures, as well as some of the information from Yole and also from Philips, and we put together a fairly comprehensive, but a high-level chart about how bulk ceramic piezos compared to CMUTs and PMUTs. So there are, of course, advantages and disadvantages for each category. So I think many of you guys know about it already. I'll not get into it here, so please just take a look afterwards. Okay, another chart from Yole. Again, thanks to Yole for providing it for us for this talk. And again, I will not get into the specifics of the how this is broken down, but the point here is that typically things are broken down by, of course, cost on one axis, and cost usually relates to miniaturization. The reason to make things small is because they cost the components that cost less, and then the other axis here on the horizontal axis is bulk versus CMUT and PMUT, and by frequency applications. So you can see, for example, the CMUTs are more suited for medical imaging, whether it's medical handheld ultrasound or sometimes in catheter, which I'll show in the next few slides here. And again, please take a look at these afterwards. So here's just a few examples. I have a few examples that we thought were noteworthy. This is actually an older paper from 2014, but it's a great example of how a PMUT array can be integrated because it's so small. In this case, on a steerable catheter. So you can see the PMUT array here at the tip. You can see the steering wire, and it's amazing how much technology can be packed into such small size. So, of course, the technology, I'm sure, is further along by now, but it's a good example nevertheless. Here, the main point is, and I give references, by the way, for all these papers here on these slides. Here's to show that, the beauty of miniaturizing MUT arrays, PMUTs, and CMUTs is that you can make them in various configurations, various designs. So, here you can actually have a bunch of them. This is a 4-inch wafer. You see a bunch of them on this 4-inch wafer. This is one of the arrays, PMUT arrays. There's three PMUT arrays here, just on one die, 10mm die. And then this is zoomed in even further. And here you can see that several elements of a PMUT array, and each consists of 10 diaphragms in this case. So very, very interesting. You can see how different configurations you can make. And the beauty is you can actually steer the beam, you can move the beam, you can focus the beam with all of these arrays. And again, I'm sure many of you know about this, but for those of you that are just learning about it, there's really a lot of flexibility with this miniaturized MUT technologies. And of course, in the bottom here, these are the package devices. And we'll have a whole talk on packaging during this webinar from Carson. This is another example, paper from 2019. Also very creative, very interesting design with aluminum nitride-based PMUT arrays on cavity SOI. So you can see the cavity SOI substrate here, and you've got the PMUT arrays on top. Okay, I want to make sure I stay on time here. It looks like I'm already a few minutes over. We have a great panel of speakers, a great set of speakers for this webinar. And what we try to do again is to make it almost like a mini conference and cover a lot of the key topics, so you can see the whole supply chain in one session. Again, we're very fortunate to have this great set of speakers with us. So I just gave my talk, and the speaker after me will be Arjun from SilTerra. Arjun will be speaking about PMUT manufacturing processes and platform solutions. So, of course, SilTerra is one of the leading foundries worldwide. They have a lot of expertise in PMUTs. They've been making PMUTs for many, many years. So Arjun will speak about manufacturing. Then we'll have Marianne Marr. Marianne is an expert, as many of you know, is an expert on design and modeling. And in this case, Marianne will be focusing specifically on PMUTs. So very good to have Marianne with us. Next, after Marianne, we'll have Ian Campbell from OnScale, and Ian will be speaking about cloud-based simulations of PMUT devices. They have a very powerful platform at OnScale, and Ian will show how you can simulate PMUTs. After Ian, we'll have Jerome, Jerome from Polytech. Jerome will be speaking about characterizing PMUT devices. So once you've designed them, once you've simulated them, once you've manufactured them, of course, you have to test them and characterize them. And that's where a company like Polytech comes in, and they already have also been working with PMUTs a lot. And Jerome will show some interesting data and information from what they've been working on. And finally, last but not least, John Miranda from Carsem will be speaking about packaging solutions for ultrasonic technologies. Of course, you need to package them, package these die to make sure that they can be integrated into the overall system or subsystem. And Carsem is one of the leading packaging and assembly houses, and they have a lot of specific expertise with PMUT. So again, we appreciate all of the speakers joining us, and I think you guys will very much like the talks. Okay, I know we always get questions about slides and recordings. So slides and recordings, a webinar recording will be available. We're aiming for early next week. On Monday, we'll be sending you an email. Please look out for an email from Jessica Ingram with the download link. I think for the slides, I think we'll be doing it via download link. And then for the webinar recording, I think it will be a link as well. So anyway, if you do not receive an email from Jessica by early next week, just give us until early next week. But if you don't receive it, then please email Jessica. You can copy myself or just email both of us, and let us know that you didn't receive that email. But again, just wait until early next week. If you don't receive it, this week, and it means we haven't sent it yet. So just please wait until Monday next week. So here are the email addresses. So very simple, Mike at microtechventures.com, Jessica at microtechventures.com. And of course, you can email me about anything else. As I mentioned, any other questions in general about what we do at Microtech Ventures, we're always welcome to hearing from everyone. And again, we have 280 participants. Checked the numbers this morning, and we had a few last-minute registrations that came in. So a great crowd, and we very much appreciate everybody joining. Okay, all right. So again, a reminder for I'll introduce Arjun as our next speaker, and just as a reminder, we'll be doing Q&A after each talk. So please use the Q&A button, the Q&A area in your Zoom screen to type in your questions. You can actually type your own questions during the talk, or you can do it right after the talk. We'll aim to have each talk for about 10 minutes, and then we'll have a few minutes for Q&A. So if you have any questions for me or about the webinar in general, feel free to type it into the Q&A area right now. Otherwise, let's get rolling with our next speaker, who's Arjun from SilTerra. So let's have Arjun. Let me stop my share, and let's have Arjun. Hi, Arjun.
Hey, Mike, can you guys hear me?
Yes, we can hear you, we can see you. And Arjun, welcome.
Thanks a lot, Mike. Give me a second. Let me pull out my presentation.
Okay, all right, very good. And Arjun is joining us from Malaysia, of course. So Arjun, we very much appreciate it that you guys were able to accommodate this time. We were trying to optimize time for everybody. But we know it's very, very late in Malaysia right now. So thanks again for joining and participating, co-hosting this webinar with us.
Yep, thanks a lot, Mike. So please do forgive me if I fall asleep. Okay, can you guys see my slides?
We can see your slides very well.
Okay.
Looks great. And Arjun, you're all set. Welcome again, and please go ahead.
Okay, guys. Good morning, ladies and gentlemen. My name is Arjun, and I'm the Senior Vice President for the MEMS and Sensors and Life Sciences BU at SilTerra. So I will be presenting today about the PMUT manufacturing processes and platform solutions. So just give me a second. Okay, so this is primarily the CMOS. SilTerra is a 8-inch fab. We are located in very close to Penang, Malaysia, and our equipment is capable down to 90 nanometers. Our capacity is around 46,000 wafer starts per month. We have been in this business for close to 20 years, and we have a clean room that's around 122,000 square feet, and it's completely a SMIF class 1 mini environments, and we are 100% ASML scanners. Okay, and in terms of certifications, we are automotive certified, and we have all the other relevant certifications also. So over the last 20 years, as I mentioned, we are primarily traditionally a CMOS technology fab, but over the last 4 to 5 years time frame, we put in a concentrated effort to look into more technologies, primarily MEMS and photonics. And one of the key advantages for our customers in working with us is that both the process development and mask production at the same site, and it actually prevents costly and lengthy fab transfers during the volume ramp up. This is one of the key assets we have, whereby we have the capability of doing the process development and mass production, so without any transfer subsequently. So today I will be talking about the PMUTs. So to just give you some background, SilTerra has been traditionally a CMOS technologies like any other 8-inch fab. We were focusing on logic, analog, RF, high voltage, and E-flash. But over the last 4 to 5 years, we put in concentrated effort to develop these other technologies, which internally we tend to call them as more technologies. One of them is IoT, power, but primarily silicon photonics, MEMS, and life sciences. So here what happens is that our customers can actually use any of these technologies, silicon photonics, MEMS, and life sciences, to build sensors. And in some cases, we also they can also build a CMOS based readout circuits using any of these technologies. And in some cases, we actually support building these MEMS or sensors on the top of CMOS. So that's what we call it as MEMS on CMOS. We have customers that do MEMS on CMOS, and we have customers that just do the MEMS and they go for an off-chip readout circuits, and we do support both the models in there. So just bear with me in terms of this animation. So here's how a PMUT device works. So this is a typical, I hope you guys can see my pointer. Just give me a second. So this is how a PMUT cell actually looks. It has a bottom electrode, a top electrode, and a piezo layer. We use aluminum nitride or scandium nitride as a piezo layer. It's just like a capacitor configuration. So the moment you electrically activate this PMUT cell, it generates an ultrasound wave, and those red, green, blue signals you're seeing is actually an ultrasound. However, based on the end applications, our customers do coat these PMUT cells with, like, for example, in this particular case, if you go for an ultrasound scan, they coat gel on you, and then the ultrasound has to penetrate through that ultrasound gel, and then the epidermis and the dermis, which is a human tissue. And at each and every interface, the ultrasound actually bounces back, it echoes back. So that echo can be picked up by the underlying electronics, and then it can be used for the processing. So that's how this ultrasound scanning works. Okay. So these ultrasound waves are generated and transmitted, and then the echo is captured. So in order to make this process available for and to address the different market segments for the ultrasound, we actually adopted what we internally call it as a PMUT platform, which is a modular concept. So to explain this modular concept in very simple terms, you can imagine these are like building blocks, just like Lego building blocks. So this is block 1, which is primarily used for interconnects. So this block allows you to have connectivity to the MEMS, and the bottom part allows you connectivity to the CMOS, and this part allows you connectivity to the external part. So if you're not doing a monolithic solution, you can disregard this connection. Then you have the external connectivity and the connectivity to the MEMS. So this one we call it as block 1. Similarly, for the PMUT devices, cavity is a key part of the device function. So we form the cavity and we call this as block 2. And then in block 3, we actually form the so-called piezo stack, which is the bottom electrode, the top electrode, the piezo layer, and the elastic layer. This we call it as block 3. And then the last one is block 4, which is pad open, to basically open the pads to the external world. So using these blocks, 4 blocks, we have the ability to build different devices. Like for example, this is a classic case of a monolithic PMUT on CMOS. For the case of easiness, I removed the CMOS, but the CMOS is typically here, and this is the top metal of the CMOS, and then this is block 1, and then we build a block 2, which is a cavity, and then the block 3 comes on, which is a piezo stack, and then you open the bond pads. So this is basically your PMUT on CMOS, right? And if you don't have CMOS, then it's just a PMUT. So using these blocks, we have the ability to build different devices with different frequencies, and that is one of our strong points. And here's a view graph of the PMUT array, how it looks after the wafers are completely processed. And this is actually a cross SEM, not cross SEM, sorry, a top SEM. And you can see this is basically the top electrode, and the bottom electrode connections are somewhere here. And in this case, the PMUT cell is circular, right? And you can use it. We have customers using different designs to do that. Okay, so that's how it works primarily. And in order to accelerate the time to market, we adopt this modular concept to primarily address different markets. So one of the key differences in this PMUT solution is that based on the market needs, the frequency changes. For example, commercial sensors, fingerprint sensors, they typically tend to use 15 to 50 megahertz, whereas the ultrasound imaging guys, the medical guys, they like to use the lower end of the spectrum, which is like 0.5 to 3 megahertz. And then we have for commercial sensors, primarily gesture control and haptic sensors, we approximately need 500 kilohertz to 750 kilohertz. So this is less than 1 megahertz. And because this integration is slightly different, we have to use a cavity SOI PMUT, but the concept of the blocks remain the same. It's still the same block 1, 2, and 4 in this case. And then for industrial sensors, you need much less than 500 kilohertz, probably 150, 200 kilohertz. And for that, we can use, we call it bulk PMUT. And in this case, the cavity is formed from the backside of the wafer, and but the underlying blocks are still the same. So with this concept of modular concept, we are actually able to address the market in a much faster way. Okay. Then, so what do we offer to our customers? Because one of the important things with SilTerra is we are a foundry. We are not a design house or a product company. So just like any other foundry doing business for CMOS or analog circuits, in the PMUT also we built it the same way. So what we offer to our customers is we actually provide them with silicon validated layout guidelines and sample GDS. Similarly, we give them layout guidelines for PMUT arrays. And if you're using CMOS, the underlying CMOS, the respective technology files. And most importantly, we actually customize the process module based on customers' design and application. Okay, this is one of our strengths. And then we also do prototyping using multi-layer masking during the customer product development phase. This is primarily to keep the cost lower by putting multiple layers on the same reticle. And then we support the customer throughout the qualification phase, pilot volume, and mass manufacturing phase. In fact, the presenters that follow me, they do talk about all of these simulation files and characterization data that basically supports this type of a concept. Okay, like these are some of the simulations we have. Okay. So key takeaways, SilTerra has been fabricating PMUTs for 5 years. The PMUT process modules are validated in production environment, and we can provide both PMUTs design and fabrication services. Uh, when I say design services, these are not full-fledged design, but basic design like PMUT cell and those things. Okay. And then customers can do the proof of concept and mass production at the same site. And we have, most importantly, we have the mindset, experience, expertise, capacity, and clean room space to support volume production for the emerging PMUT devices. So that's my last slide. I'd like to say thank you, but I think most importantly, I want to thank my partners. I simply want to tell them that this was not possible without you guys. Okay. So thanks a lot for your support.
Arjun, thank you very much.
Thank you.
Thank you very much, and great presentation. Yeah, please keep up this slide, and we can take a few questions. And by the way, great job on staying on time.
Okay, thank you.
Thank you very much. All right, we can take a few questions. So some of these are quite specific. So Arjun, some of these questions maybe would be good to defer, to later if you don't know the specific answer. But let's try a few of these. What kind of electrode materials are used for PMUTs?
We have customers that use some use molybdenum and some use aluminum. So we have experience with both of them.
Okay, very good. Another specific question, what is PMUT cavity depth and frequency?
Well, I can't reveal the depth as such, but frequency, as I mentioned, we have the ability to create from all the way from 200 kilohertz to 30, 40 megahertz. I showed that on the slide.
Very good. That was a great slide, how you
Yeah.
had the frequencies and the applications. So that was very good. What's the minimum piezo thickness you can deposit? Another
Well, that's a good question. We never really tested out what is the minimum, but for sure we have gone down to 4,000 angstroms, 5,000 angstroms. But I'm sure the tool is capable of depositing even thinner films if there is a need for such application.
Okay. All right. Very good. Yeah. So that's great, Arjun. These are specific, very specific. Why don't we do deep backside edge in high frequency device for greater than 1 megahertz?
Yeah, that's a good question, but I think we primarily do it for keeping the cost minimum. Okay, and that's part of the architecture. Okay, sorry, I can't give more details on that, but that's a part of the architecture, the device architecture.
And by the way, of course, Arjun is sharing here the contact email, but if for whatever reason you somehow can't get in touch with SilTerra, you should be able to, of course. We're happy to put anyone in touch with SilTerra for further discussions, as well as for all of the other speakers. So we're here to facilitate and make sure the connections happen. All right, we have a lot of questions.
Oh my God. Okay.
This is, I just scrolled down further. So this is great. We really appreciate the audience being so engaged and having all the questions. Let's do one more, and then we'll go to our next speaker. But
Okay.
what we will do, we will save all of the questions and we will share them with the speakers so that hopefully the speakers can address the questions afterwards. And again, if somehow that, something gets lost in the shuffle, please email us or email directly here, the email address that Arjun is providing, and get in touch with SilTerra. So let's just do one more. Does SilTerra offer shared wafer services, for example, multi project wafers to enable prototyping with small budgets?
Yeah, we do. We do. That's what I said. One of the things I mentioned is that we do multi-level masking and others. So we do that.
Excellent. Yeah, so, well, very good. Arjun, again, great overview talk. Thank you very much for staying on time. For everybody, again, the contact information, email address is
So
here.
yeah, thanks. I'll stop sharing. Okay. So you guys can move and move.
Very good. Yep. And then Mariana's here. Arjun, thank you very much. And
Thank you. Thank you.
let's bring up Marianne. Thank you.
Hello, everybody.
Hi, Marianne.
Hi, can you, I'm sharing my screen. Let's see if you
Yes.
can, are my slides showing okay?
Slides are showing great. Marianne, we can see you. How are you doing, Marianne?
I'm good. Greetings from California.
All right. Greetings back from Michigan. Good morning. Good morning to you, and thanks for joining us.
Sure. I'm Marianne Mayer. I'm the CEO of SoftMems. We provide design tools and services to the MEMS industry. And I'll be speaking to you today about the design aspects of MEMS PMUT devices. And I'll be followed by my colleague, Ian Campbell. So we're kind of tag teaming. I'll talk about design. He'll talk about simulation. And so Mike asked me to talk about what are the key design trends for PMUTs. And so I've listed a bunch of them here. Let me go through them. One of the things we noticed, which is very exciting, imaging arrays are really getting larger and more complex. But yet at the same time, we are seeing a lot of smaller form factors for handhelds, which is creating some interesting design challenges, especially in packaging. And one of the things that we're also seeing out there is some materials engineering. There's a lot of interest in things like scandium doped aluminum nitride. So there's some engineering going into what materials we're using to make the PMUTs. And one of the things that's happening is as we are trying to make better and smaller devices, we need to analyze these devices for their acoustics, their mechanics, their electrostatics, and they're all coupled together with coupled fields. So that's why what Ian will talk to you about is so important later. And SilTerra is in a really great sweet spot now because integration with electronics is also a key design trend. How we put these things together with Arjun talked about various ways of making electronics and the PMUTs together, and they've got an integrated platform. But the design implications here is that we really want to co-design the PMUT and the electronics, and we want to look at how the parasitics transfer from one to another. And SilTerra really has that worked out with their PMUT devices built on top of CMOS. And one of the other key design trends is as these PMUT based products are being brought to market is companies really want to do more than one market. They want scalable IP. They want to be able to redirect their PMUT designs to new markets. And as Arjun pointed out, the frequency of the PMUT depends on the application. So really having a scalable IP and being able to retarget based on new frequencies is very, very important. So those would be my top key design trends for PMUTs. Now let's talk about some of the design issues for creating these devices. And the first one has to do with fabrication. One of the things that we note is that MEMS has process variation across wafers. So, and often this variation can be radially dependent with position on the wafer. And this impacts the device performance across the wafer. So for example, the depositions could be thicker in the middle than on the end. So we really have to look at at, it from a design perspective, we have to look at, what these variables are and how they depend, what that variance is and how they depend on wafer position. There's other types of variances that are mask dependent. They might be edge dependent. They might be scan dependent. Probably the most important one for us is this thickness variations. And so what we've done to help SilTerra's designers is to create what we call a digital factory. We've worked with SilTerra to look at equipment variance, process variance, the wafer and material variance, and with OnScale, we can help predict the performance variation based on these the variations that are fab related. And so we can use what's called a digital twin to relate the manufacturing variation to performance variation. And so what are these key process and material variables specifically for PMUTs? So in the SilTerra PMUTs, the aluminum nitride thickness, which is your PMUT piezoelectric material, is very important. They do a silicon nitride on top, so that thickness is very important. And we want to look at the thickness variation across the wafer. And then we have the variables of the process, but what are the important material properties? In order to do good simulations, as Ian will tell you next, we really have to have accurate material properties. And so the key ones that we want to look at for PMUTs are the piezoelectric coefficients for the aluminum nitride. It's a piezoelectric material, so we have to look at the piezoelectric matrix, Young's modulus, things like that. We also need to note that the film characteristics vary with deposition conditions. So we've worked with SilTerra and they've taken measurements and shared them with us so that we can characterize the material properties so that we can get really good simulation results. And one of the things that also Ian will point out is that once we have the PMUT understood and its material properties, we have to look at what's loading the PMUT when we are simulating it in situ in an application. So for example, you'll see later some results in air, and we'll talk about how those work, but then there's also the materials that the PMUT may be interacting with, water, for example, and a popular one, fluorinaire. And so we've talked about material properties, we talked about the fabrication, but what about what the designer controls? And these are the PMUT design variables. So as we mentioned, we have different frequencies for different applications, but the key design variable here is the different membrane sizes. So we change the membrane size to target different frequencies typically. And so we need to, as designers, look at what we call a nominal device, like the device that we would like to target for a particular frequency. But we have to look at how that nominal device might vary due to things like the mask biases or the tolerances on how those devices are laid out and fabricated. But then we also may want to look at different geometry sizes to target different frequencies. So we've got to look at different design variables there. And then we also, once we've chosen our membrane, we may want to look at optimizing the membrane shape, how it's anchored, the aspect ratio. So we optimize the membrane shape and size for a given application. The other thing that we want to do is look at how our geometry and our given topology for our membrane is going to work mechanically. So we want to explore what the membrane displacement is going to look like. Arjun showed you the cartoon of the PMUT emitting waves. So we want to understand how the membrane works as it moves up and down, or the so-called pistoning effect. And then finally, part of the element design is also the design of the electrodes that are going to be bringing the signals out to the PMUTs. So this is what we care about when we're looking at an individual element. But as it was mentioned, there's a lot of applications where we have arrays of PMUTs acting together to solve a problem. So here we want to look at things like the array spacing. We want to optimize how we put together the array elements for power, for example, for phasing. And one of the things that we really need to look at is how the cells couple to each other. And Ian, and also we'll see in measurements later, how we lay out the cells and how they couple together can cause unintended consequences, for example, causing frequency and phase shifts. And so one of the things that we do in order to create a design environment for the designers of the PMUTs, SilTerra's customers, is that we model that fabrication process. So we model the fabrication process above the IC layers. As Arjun pointed out, we have an interconnection layer, which we measure, we model, and then we model the PMUT, the cavity, and then its final interconnections. So we create these 3D models from the masks that the customer designs or from test structures from SilTerra and a description of the fabrication process that Arjun showed you. And so we get these process parameters and sequences from SilTerra, and we then create a unique model for mask bias and geometries. And then this PMUT model that we've created, we've shown one as an example here with the cross section on the right. These are based on actual information from SilTerra. We can send a fab accurate model to OnScale for simulation. And so they'll be able to predict the performance based on a given mask set, based on the fabrication process that you've chosen from SilTerra. And so all of this information is then rolled up in what Arjun talked about a little bit, which is the PMUT design kit that you can get from SilTerra. This design kit acts as a bridge between the designers and SilTerra. It's a way to give a standard information exchange of the information. So it cuts down on communications mistakes. So because SilTerra can share with you information in a standard way. So the design kit includes things like mask information, fabrication information, the materials, the wafer information, and in some cases can include programmable device layouts and models for those characterized devices. And in this way, if you use the design kit and you work with SilTerra, you can have create a variation tolerant design via the design rules that they give you to produce successful devices. So at this point, I think I've given you some food for thought about what's important in terms of design of PMUTs, and I'll turn it back to Mike and our subsequent talk.
Yeah, Marianne, great job was the talk. Very, very nice, and tons of great information. And thank you for staying on time as well. This was really great. Okay, we can take a few questions, and we have a few questions already coming in. Again, these are quite specific. What are the differences between aluminum nitride and scandium dope aluminum nitride regarding the applications?
Ah, interesting. Well, that's one of the things that you know that people are trying to optimize right now. The original, of course, people were using aluminum nitride, but now they're trying different dopings, and it's interesting that we're finding that based on the application, you may target different doping levels, and that creates an interesting question for the people who are trying to supply targets, because we're not standardizing on a particular doping amount. So it's quite interesting out there that, that this is still food for thought in terms of what the appropriate doping levels are. So I think SilTerra is going to probably the best person to answer that question on what they're going to offer. But the thing that's interesting is this is still something that's being optimized within the community on an application by application basis.
Okay, all right, very good, great question. Let's take a few more. How does intrinsic material stress influence your membrane performance? For example, the position of the neutral axis and the curvature of the membrane over the diameter.
Yeah, so this is really interesting. We've seen a lot of interesting papers out there in the literature about different electrode configurations and different anchoring structures, different anchorings. And one of the things that you know, you should do, I'm kind of stealing Ian's thunder here, but do simulate. You'll be able to get stress plots of, you know, and also displacement plots of how the stress affects the deformations and the motion. And this is also something that you can explore. When we hear the talk from Polytech, you'll be able to see what those things look like actually in real time. But yeah, that is definitely something that we need to look at. We have initial stress values from the films. So there's an initial value for the materials before the PMUTs are moving, but then we also have to look at how the stress affects the shape, the nominal shape before it's moving, and then as it moves. So this is something that we have to track over temperature as the devices are fabricated at SilTerra. Stress can change as other layers are deposited on top of the PMUT structures. So the best way to really get at that is both experiment and simulation with OnScale.
Okay, very good. Let's do one more. We have more questions coming in. Again, great audience. Let's do one more. So in the past, Marianne, people used to use frequencies near 200 kilohertz for gesture recognition, consumer applications, commercial applications. What is the reason for increasing this value to 500 kilohertz to 1 megahertz band?
Okay, so you're looking at different performance metrics, right? So one of the things that people noticed is that they're getting better performance. Oh, sorry, I guess Ian's setting up here. You're getting better performance at the other bands, and so there's a number of KPIs, and Ian will talk about that in his talk about what we're looking for and how we look at the performance of PMUTs. And one of the things that you'll see is how that's based on frequency. So hopefully when Ian talks about it, maybe some of the pictures that he'll show may be able to address that a little bit.
All right. Yeah, very good. Marianne, great job. And we have more questions coming in. If we didn't get to your question, we will share your question with the speaker. And by the way, if you choose to stay anonymous with your question, then we can't match you with the email address. So, if you want your question answered, especially afterwards, then we encourage you to actually provide your name because we will share all of the questions for each speaker so that they can hopefully, they will certainly try to attempt they'll try to address all of your questions afterwards. So again, great questions. Marianne, fantastic talk. Thank you very much for joining us. We really appreciate it.
Yeah, sure. And as I said, I'll be happy to help answer questions later as they came in. Thanks a lot, guys. And I'm looking forward to Ian's talk and the rest of the talks. I'll be here.
Very good. Very good. Very good. Thank you, Marianne. All right, Ian, looks like your slides are up, and let's turn on your video. Here we go. Ian, how are you doing? Good morning.
Doing well, Mike. How are you doing?
Doing great.
Awesome.
All right, doing great. All right, so everything is looking good. We can see you, we can hear you.
All right.
Slides are looking good. So Ian Campbell, OnScale, will be speaking about simulations and picking up on the topic of design that Marianne just was discussing. So Ian, welcome again, and please go ahead.
Yeah, thanks a lot for inviting me to this. This is really exciting. It's been amazing to see the growth in the PMUT industry and all the applications that PMUTs can cover. And it's been very exciting to play a small role in that growth. First, I'd like to tell you, quick blurb about me. I'm a Georgia Tech grad. I founded a company called Next Input in 2012. It sold to Corvo recently. So I've been a MEMS designer, MEMS engineer. I've been in fabs making MEMS devices, and I've learned the importance of simulation in the MEMS R&D workflow. I started OnScale in 2017 to solve some of the problems with simulation of some of these complex devices. And we're promoting what we call digital prototyping of MEMS, and soft MEMS, and Marianne is a huge part of that. And the idea with that is simple. It's, if you can digitally prototype and digitally qualify and understand the performance and yield of a MEMS device before you go take it to a foundry, you could potentially save a lot of risk, cost, and time to market. So I'm going to be talking about how to do that, and specifically with PMUTs. So let's talk about the digital foundry workflow. The workflow usually begins with an EDA tool like Siemens EDA or another MEMS layout tool. and you would lay out your mask set using that 2D layout tool. That's kind of what we call a digital twin of a device design. Then you would take that layout, and just like Marianne just showed you, you would use SoftMems, MEMS-Pro to create fab accurate 3D models of that layout, and not just the nominal values, but also factoring in some of the tolerances, because every design variable here, including the top-down orientation, the layout itself, and the thickness of each process step or layer, will have a tolerance associated with it. And you get those tolerances, by the way, from your foundry partner. So you'd go to SilTerra, for example, and SilTerra knows exactly what the tolerance bands of each of their processes are. Then you create a set of 3D models. In a digital twin or digital prototyping process, you wouldn't just create a nominal design and simulate it, but you would actually create many 3D models of a potential design to look at all of the potential outcomes of an actual manufacturing process. When you have that population of models, is there a question, Mike?
Yeah, hey, I'm sorry to interrupt. Very sorry to interrupt. Looks like your slides are not advancing. We're seeing the first slide, but we're not. It's not going to the next.
Oh, really? Okay. So you're still seeing like the title slide?
We're still seeing the title slide.
Okay.
Yeah, exactly.
Let me stop sharing, and I'll try to reshare. Let's see.
Okay, sounds good. Yeah, let's try that.
Sorry about that.
Yeah, no problem. Sorry to interrupt. Yeah.
No worries. Thank you for interrupting.
Yeah.
All right. How about now?
Here we go. So now we can see about the speaker.
Yeah. Okay. You
Yep.
can see the stuff popping up.
That's great. Yep.
Okay. Great.
Now digital foundry workflow. Here we go. Thank you.
All right. Thank you. Thank you, Mike. Appreciate that. So yeah, we covered doing your layout in a tool like Siemens EDA. SoftMems will take that layout, create fab accurate 3D models of not only the nominal design, but also the process variation that you can expect. Then you'd have a population or a batch of 3D models. And finally, you would use OnScale to simulate those different 3D models. In this case, these are PMUTs. You can either simulate individual cells, or you can simulate an array, like what we're showing here. That's being, there's like a beam forming pattern moving across this array. And if you follow this digital prototyping and digital qualification workflow, ultimately you can understand how your device will yield, or you can go back and tweak the design to make it more robust and improve potential yields when you move on to actual fabrication stages of the R&D process. So let's talk about some of the device parameters for a digital qualification study. And Marianne alluded to some of these, but these are just a few things that would affect the key performance indicators, KPIs, of a device like a PMUT. The first thing and most obvious thing is the cavity diameter. That's going to affect your natural frequency or resonant frequency. The top and bottom electrode thicknesses will impact performance. The piezo layer thickness, of course, will impact performance, and the elastic layer thickness will impact performance. So the first step is to parameterize these geometric variables. And then you can use a parametric sweep to match experimental electrical outputs or experimental results to your simulated results. So when we are simulating these PMUTs, we look at things like the resonant frequency, S parameters, Q, capacitance, impedance, and mechanical displacement. We can use things like a Polytech laser vibrometer to actually detect displacements, which is pretty cool. I'll show you how that works in a minute. And then ultimately, we want to simulate and match some empirical data that we've got from an early prototype, and then use that simulation or those simulation variables to then do our digital qualification study and look at lots of different potential designs. And our simulations will analyze these outputs, resonant frequency, displacements, etc. Once we've tuned our simulation study, then we can begin to look at the effects of process variance on the nominal design. And there are multiple different process stages to create a PMUT that ultimately create multiple different layers in the MEMS stack. And each of those layers will impact performance. in a subtle way. When you start adding them all up, you get combinations of tolerances that will impact performance. So this is just a simple study where we took 1,000 different variations of that single PMUT unit cell, so single diameter, but we varied things like the diameter tolerance, the thicknesses of various layers, et cetera. And then we just plotted the results. So this is actually our inputs. Our inputs were the thickness of a piezo layer and thickness of the elastic layer. And then this is the population that we simulated. You can see that we've got a pretty nice distribution in both of these different parameters. Now, these are the outputs. This is what actually happens to your resonant frequency, to sensitivity, and to capacitance. So I like to think of this as, instead of going and actually manufacturing 1,000 different PMUT cells on a wafer, or actually creating, a much, much larger physical population of devices and then testing them all, instead just simulate a population of devices and see what the impact is to your KPIs. And we still don't know yet whether this variance is good or not. Let's say, sensitivity has a particular range. We don't know if that's out of band or not acceptable. So let's take a look at what we do next, which is to actually start looking at what the targeted KPI is, and then what we consider our pass-fail criteria. So once we start adding in our pass-fail criteria, you can see we're getting a drop-off in some of these device designs. So at the edges of our process tolerances, which again will create geometric and material property tolerances, we're actually having some fall off. So now the engineering team can decide, hey, should we go back and either relax some of our KPIs, maybe our target KPIs are too narrow, or should we go back and tweak the design in order to get better yield, or should we go talk to our foundry partner and see if they can narrow their process variation a little bit to give us better yield. In this case, this was an example to intentionally look at a bad device design that wouldn't have a good predicted yield. But understanding this up front at the design stage will save you, potentially millions of dollars in physical prototyping costs, potentially years of time in your MEMS R&D cycle. Let's take a look at how we correlate physical simulation or physical experimentation data with simulation data. So this is just one example. We took the S parameters from a set of devices and compared them with the simulated devices. So this is a comparison of actual versus simulation. And as you can see, the simulation is giving us a pretty good correlation with experimental results. Our simulated resonance, for example, was 21.75 megahertz. The experimental resonance was 22.65 megahertz, about a 4% deviation there. And that may be because we don't really know what the actual geometry and material properties were in our experimental sample. We do know what we put into the simulator to get this result. So just the process variance could explain that difference in variation. Next thing I want to show you is how we can start to use 3D simulations and large array simulations to do things like create beamforming algorithms. And this is another nice feature of being able to simulate before you go build a bunch of prototypes. Algorithm engineers love to get physical test data in order to create their software algorithms to correct for things like cell-to-cell variance, or to test different beamforming approaches. But instead of using a physical test sample or an engineering sample to create those algorithms, you can actually just simulate these large three-dimensional arrays and give that data to your algorithm engineers so that they can create their beamforming algorithms. So in this example, we had an array of PMUTs, which you see at the bottom. And the goal was to produce a beamforming pattern that had an amplitude, largest amplitude right above this array. And that's what we're showing here. And we can actually make sure that we're getting maximum amplitude of a pressure signal at, I think this is a fingerprint sensor. So you want maximum amplitude on this curved surface. And then we can actually look at the return signal that each of the PMUTs will receive, and then create our beamforming and fingerprint detection algorithm without ever making a physical prototype, which is pretty cool. Other thing I want to kind of set up for Polytech is correlating some Polytech physical test data with simulation data. So we actually did a much longer version of this presentation with Polytech and Siemens EDA on digital qualification. And I took one piece of that to show you today. And this was about the edge effects of a PMUT array. So as these, the cells get closer and closer to the edge of the array, you'll start to see some effects that can be measured directly with a Polytech laser vibrometer and can also be simulated with OnScale. So I'll show you the results of that simulation, and then our Polytech friends will actually show you the experimental data that they collected. And you'll see that they're very similar in terms of the response. So in this example, we've got a boundary that's representing the edge of our array. And then we have a symmetrical boundary condition and an infinite boundary condition in the, I'll call it the y-axis. So a boundary in the x-axis and infinite boundary condition in the y-axis. And you can actually start seeing how you're getting some of these edge effects as we get closer to that boundary. All right, so ultimately, this type of approach, using SoftMems, using OnScale, and then also, working with your foundry partner like SilTerra to understand their process variation, enables digital prototyping, and digital prototyping of MEMS and specifically PMUT devices massively reduces risk, cost, and time to market.
All right. Yeah, Ian, great talk. I very much like the beamforming. That was a really cool simulation and great talk. So we can take a few questions here. Let's see. How accurate is your simulation compared to real values? So for example, frequency, capacitance, or sensitivity.
Great question. We get that question, every time we promote simulation. And I'll say it's as accurate as your input values. So think of a simulator as a calculator. It's going to give you 2 + 2 = 4 accurately, but you have to know what parameters to input. And very often, engineers don't know what their actual material properties are. They don't know what the actual geometry of their device is. That's why it's very important to be able to do parametric simulation studies to look at broad spectrum of potential outcomes. And very often when we do a parametric study, the empirical test data that they have falls within that spectrum. So that's what I refer to as like tuning a simulation tool. If you don't know what your actual parameters are, you just do a parametric sweep and you find the closest match. And if you can get within ±5% of the actual experimental performance, that's usually good enough.
Okay. All right. Very good. Good question. Let's do a couple more. Can you explain the difference with FEM simulators? So, for example, compared to COMSOL, how do you guys compare to COMSOL?
Well, it's like comparing a calculator to another calculator. Like we'll both give you the similar answers if you put in similar inputs. The difference between OnScale and COMSOL is a desktop simulation tool, whereas we are a cloud simulation tool. So we can actually run 1,000 simulations in parallel on a cloud supercomputer, and you get those answers back 1,000 times faster than if you were running them one by one on a desktop computer. That's the primary difference.
And Ian, I believe your pricing is also scalable. So depending on compute hours, right? And I think people can get rolling. I mean, everything is based in the cloud. So people can get rolling very quickly at little to nominal cost.
That's right.
There's not a big upfront investment, right?
That's right. There are no software licenses, we think about things in terms of subscriptions. And you're right, Mike, you can start for free and then buy core hours as you need them. You can buy a lot of core hours in one quarter because you're doing a big R&D project. Next quarter, you might not need the core hours, so you don't purchase them. It's very scalable.
Yeah, very good. Yeah, so I think that's a big difference. Okay, great. Let's do maybe one more. And again, great to see all the questions coming in. Does OnScale support nonlinear acoustics? Are we able to detect nonlinear echoes while performing pulse echo using nonlinear transmission?
Yeah, it depends on the definition of nonlinear. We do all of our simulations in the time domain, so we're able to detect nonlinear effects and transient effects very well compared to a frequency domain solver or static solver. So like I'd have to understand the specifics of the simulation, and we're happy to address the specifics. You can reach out to us at onscale.com and we'll talk about that.
Okay, let's squeeze in one more, just because I think it's a really good question from Joshua Lee. How much computational resources were required for the beam forming simulations? And I know it's quite specific, but
yeah, that's a great question. Some of the unit cell simulations that I showed you, when we're running 1,000 of them, those are on the order of less than a core hour or CPU hour. The large 3D array, when we were testing beamforming algorithms, that was on the order of 1,000 or more core hours. So obviously, the more complex the simulation gets, the more expensive computationally the simulation gets, but it's still a fraction of the cost of actually going and prototyping one of those devices, putting it in a lab, getting data from it, then testing your beamforming algorithms. The cost of doing all of that is massive compared to the cost of running a simulation.
Okay, all right, very good, and great questions. The audience has been great, and the speakers, you guys are doing a great job as well. All right, Ian, thank you, very nice talk, and let's now bring up, so Ian will stop his sharing, and then let's bring up Jerome. I can see Jerome. Jerome, how are you doing? Good morning again. Hi, Jerome, you may still be on mute, so here we go. I think you're off.
Can you hear me now?
Yes, we can hear you now, and we
Excellent.
can see your screen. Very good. How are you doing, Jerome?
I'm doing good. Thanks for the introduction. Very interesting talks. I intently listened to everybody's content. And I like the flow, how this all kind of flows together in this presentation.
Absolutely.
Very nice mini conference, as you put it, Mike.
Yeah, very good. Again, you guys are doing a great job, and the talks are very complimentary. And I agree, the flow is very good. So Jerome, again from Polytech, Jerome will be speaking about characterization of PMUT devices. So of course, when you make the actual physical devices, you want to study them, you want to characterize them, you want to test them. So Polytech is one of the leading companies, and it has a lot of expertise with PMUT specifically. So Jerome will be talking about Polytech's capabilities and also what they can do and have done with PMUT. So Jerome, everything is looking good. Welcome again, and let's roll, and please go ahead.
Thanks, Mike. I'm Jerome Eichenberger, Business Development Manager at Polytech, and we specialize in laser-based non-contact methods for capturing the mechanical response of structures in the macro world as well as in the micro world. In this particular instance, we will focus on the characterization of PMUT devices, as Ian already indicated. We've been in touch with Ian and his team at OnScale and discussing on how what kind of data we should generate to strengthen and fine-tune the models he's providing to his customers. And then we got in touch with SilTerra, and we've characterized some of the PMUT array devices for them, just to kind of for a proof of concept. And I'm going to show the data live here in a little bit, but I'll start with a few introductory slides. Okay. So why characterize the direct mechanical response? In ultrasonic imaging, the quality of the picture can be compromised because of manufacturing variances leading to wavefront errors, for example. Knowing the actual dynamic behavior of the PMUT gives the engineer the right feedback to optimize the performance, like efficiency, for example. Having accurate characterization data enables fast design cycles, as the model can be perfected in very few iterations. Accurate model validation requires knowledge about the direct mechanical response. Acoustic and electrical tests also provide valuable information, but are not ideal for the mechanical validation. As you can see in the animations on the right, we measure displacement at one location and also across an entire grid of points. Measuring amplitude in the nanometer or even picometer range are not a problem, and we reference the response to the applied voltage. The critical performance parameters typically are element-to-element crosstalk, uniformity in piston mode response, uniformity in deflection shape, and efficiency, as well as sensitivity. How do we characterize PMUTs? A laser Doppler vibrometer is built into a custom microscope setup, allowing us to view the sample while at the same time steering the laser beam across the surface for measurement. This allows us to measure the direct mechanical response with high resolution and bandwidth. So we have a flexible product offering where we are able to measure frequency responses from just DC or pseudo DC at very low hertz up to kilohertz, megahertz, and even into the gigahertz. The lateral resolution is determined by the diffraction limit of light. We're using visible light in this case, so we typically get the laser spot diameter of 1 micron or slightly below that. The displacement resolution depends on the frequency range, also depends on the surface, but it's typically less than 1 picometer. So let's switch over to an actual data set on a PMUT array provided by SilTerra. I'm going to switch over. I hope that works well. So you should now see the software interface. If you could just provide feedback real quick that you see that switched over. So in this interface, you see data that has been captured on a PMUT array. These are 80 micron diameter PMUTs that you see here. You see the camera picture that we took, and overlaid is the actual measurement data. We have, in this case, we have taken 37 measurement points on each element, so 370 measurement points across 10 devices. And what we're looking at on the bottom is the frequency spectrum at one particular point on the element that I have highlighted here. The scanning in this case is very fast. I mean, I'm referring to scanning point to point because we're at very high frequency. The frequency resolution was 1.25 kilohertz. So measuring all these points took less than half a minute. Now in the plot here, you see that we're in the picometer range. You might be wondering why the displacements are so low. It's because we apply a broadband excitation. We are exciting frequencies from 0 up to 10 megahertz, so that the excitation energy is distributed across all these frequency lines. Now, if we switch over to a frequency response function, we're going to see that the displacement per volt is in the order of, in this case, 2 to 3 nanometers. So 2 to 3 nanometers per volt, are we talking here, at the resonance frequency of this device. As we move and highlight measurement points closer to the edge of an element, we can see how the amplitude drops as expected. What we also see is there is variation between elements. So if we look at an adjacent element, we see the resonance frequency as well as the amplitude changes. Now, these are measurements that have been taken in air. Obviously, when there is a couplant or liquid, the damping increases and the variations are less noticeable. Now, what we also see here in this example is some crosstalk. if we go back to this device, we see the resonance frequency is around 5.8845 megahertz. I switch over to this device and I kept the cursor at that frequency from the adjacent device, and we see a little hump in the transfer function of that device. So that indicates there's a little bit of element to element crosstalk. Now we can also look at devices up here, and we can see that there's some variations. It's a little exaggerated because I zoomed in quite a bit on the frequency scale. We can then also animate the measurement, the measurement across the scan grid, and we're animating the structure at the frequency of where the cursor is located. So as I move the cursor around, we're animating now the frequency wherever I'm dragging the cursor to. We can show this in a pseudo 3D view, so we have a better idea how this moves in space up and down. And we can also look at a profile view of the same measurement. So if I zoom in here again, I've drawn a profile across the bottom row of elements. And on the bottom section of the screen, I can now see the animation of the profile across these 5 elements. I can change the frequency up here, and we'll see how the animations change accordingly. So I'm switching back to the presentation and coming to my conclusion. So basically what we learned is that the mechanical response measurements help characterize element-to-element crosstalk and other critical parameters. Polytech laser vibrometers capture the full field displacement response quickly and accurately. And accurate validation data enables engineers to optimize the design cycles of PMUT development. And this brings me to the end of my short presentation. At Polytech, we're a metrology company, as you can see. We provide instrumentation, but we also have a strong team of technical experts that can help you with your specific application. We offer testing services and rentals, and also flexible leasing options. So at this point, I think we can go over to answering some questions.
Yeah, Jerome, great presentation, and thanks for sharing your email address here so people can contact you. And yeah, a great job. It was a mini live demo, so that was impressive too. So yeah, we have questions coming in. Great audience, you guys. All right, so Jerome, we can take a few. So question from Amir. Hi, Jerome. Not sure if you mentioned if the device was packaged or not. Thanks. The device that you showed.
Oh, thank you. No, that was not packaged. It was a cut die device that we put directly underneath our microscope system, and we used probe needles to power the device. We've worked with probe station providers in the past and also recently. So if you want to measure an entire die, we can help you with the integration of our measurement tool onto a probe station.
Okay, very good. Next question. Can we perform the laser Doppler vibrometry measurement on immersed PMUT arrays?
Yes, we can. So as long as there is a visual access to the device, meaning that if the fluid or the liquid is transparent, and we can see the laser beam on the structure and we get light back, we can measure. We're basically capturing the returned or the reflected light from the structure, and we demodulate the Doppler shift in frequency that has been introduced by the motion of your test structure. When you measure on submerged structures, you have to make sure you don't get interference with the reflection of the water surface or any other optical surface that's in the light path. But with careful alignment and arrangement of the setup, this is by all means possible.
Okay. All right, very good. Another question from Amir. The other question I have is about the three-dimensional displacement and the possibility of characterizing that. Thanks.
Three-dimensional displacement, so I assume you're referring to characterizing the displacement up and down versus also in the in-plane direction, X and Y.
Right.
For that, we have two different techniques that we can apply. One would be to use a 3D vibrometer that measures the Doppler shift not just in the vertical direction, but also at an angle in the lateral direction. For that to be successful, though, we have to have a certain amount of roughness on the surface, so that we get stray light that we can then use to measure the in-plane components. An alternative method is a stroboscopic method that we can also integrate into our microscope characterization tool that uses, as I mentioned, a stroboscopic approach to measure the in-plane movement, uses pattern matching, and we can then resolve any movement with subpixel resolution because we're using a grayscale analysis of the individual images.
Okay. All right. Very good. And let's do one more question. We have more questions coming in, but let's be sure that we sticking to time as much as possible. And by the way, before we go to the next question, I just wanted to remind everybody that, especially for those that are putting anonymous for their questions, if you want your question answered, if you could actually share your name, we will be sharing all of the questions afterwards with each corresponding speaker. So if you share your name, then we'll share obviously with the speaker. If you're anonymous, we can't share your name and email address. So, but also alternatively, feel free to contact Jerome via email as he is sharing here. So either way works. All right, Jerome, let's do one more question. So. In order to measure a different location, does the stage move or does the laser move in your setup?
The answer is both, depending on the geometry. So we have steering mirrors inside our microscope vibrometer system that allows you to steer the beam within the view of your image. And depending on the magnification of the objective that you're using, the view is either bigger or smaller. Now, if you need to scan or reposition your measurement location beyond the view of the microscope image, and then we can employ a stage. So we usually integrate a stage together with that system to measure, across a wafer, for example, but or larger structures as well. So the answer is you can do both.
All right, excellent, very good. And again, we have more questions coming in. Very good to see this. Jerome, great talk, very, very nice, and also a great Q&A. So Jerome, thank you very much again.
Thanks a lot, Mike.
All right, thank you. All right, let's bring in now, so Jerome will stop sharing his slides, and now let's bring in John Miranda from CARSAM. John, can see you. Looks like you're still on mute, so if you could unmute yourself, and here we go. We can see your slides now if you want to put them in presentation mode. Here we go. Yep, it's right there. That's right. Yep.
Thank you, Mike. Yeah, we got it.
All right, great. So just a quick introduction. Dr. John Miranda is VP of Business Development and Sales at CARSAM, and again, we wanted to show the full cycle. So now you've seen the fabrication part from our June. Marianne and Ian talked about design and simulations. Of course, Jerome just spoke about characterization and testing. And so finally, last but not least, you also need to package the device. And CARSAM is one of the leading companies in this area. So John's talk is going to be about packaging of PMUT devices. So John, everything is looking good. We can see your slides. We can see you, we can hear you. Welcome again, and please go ahead.
Thank you, Mike. Well, what a great group of tech talks. All of these topics are critical to a PMUT advanced packaging design. First, I want to thank SilTerra and Microtech Ventures for inviting me and the Carson team to speak today about advanced packaging technologies for PMUT devices. Second, I'd like to say it's an honor to be speaking with you today, the PMUT industry, as I reached out to many of you, your CEOs, your CTOs, and leaders in engineering, with the intention of understanding your PMUT packaging and testing needs. While many large PMUT players have a path to advanced packaging solutions, still a majority desire support from the package concept phase to high volume manufacturing. Therefore, if we've not connected, please know that my door is open to you and that Carson is ready to collaborate with you. So it was in 2019 at the Microtech conference that I had the pleasure of hearing Mr. Kantamahati speak about SilTerra's prowess in PMUT and MEM sensors. At that time, we saw a great opportunity to collaborate and partner with SilTerra. Since then, Carson and SilTerra have engaged in PMUT packaging technology development. Carson's vision is to offer customers an optimal path from silicon design through to PMUT package production via a tight collaboration between SilTerra, Carson, and you, the customer. The value proposition being that a PMUT customer can take advantage of this integrated services relationship that offers optimal customization, time-efficient design cycles, which can free up resources and time, resulting in a faster path to production and time to market, so that you can capture market share and shorten the time to generating revenue. I want to take this opportunity to share a bit about Carson's background. Carson has over 45 years of experience in the outsourced semiconductor assembly and test industry. Today, Carson is one of the most trusted and recognized names in this industry. Our parent company, with a strong banking history, is the foundation for Carson's strong balance sheet and financial stability, which means that we're always ready to support our customers' growth. Carson is an operating company within Malaysia Pacific Industries, which in turn is part of Hong Leong Group, one of Asia's largest, most successful conglomerates. Malaysia Pacific Industries' stock symbol is MPI and is traded on the Kuala Lumpur Stock Exchange. Now, Carson operates 3 flagship factories. One in Suzhou, China, and 2 in Malaysia, Ipoh, Malaysia being the home of Carson's MEMS and sensor unit, where PMUT package development occurs. Now, Carson may not be the biggest OSAT, but we rank among the best. And it all begins with our talented team and our cutting-edge technology. We continue to invest in state-of-the-art assembly and test equipment and in Industry 4.0 technologies. Today, we are a preferred first source to many of the top 10 and top 20 global MEMS suppliers. Our teams are hyper-focused on our customer success. We have a collaborative spirit. We are a transparent company, and we work from day one to earn a customer's trust. Now, in this next slide, I've extracted key packaging technologies that are applicable to PMUT, which I believed would be beneficial to you. Turning our attention to SIP, System in Package, PMUT packages are the epitome of a system in package. The reason being they transmit and receive acoustic wave energies, and they also can incorporate logic, such as system on chip, on CMOS, or incorporate a companion ASIC. With SIP technology, one can leverage the assembly of multi-die packages, either in side-by-side or stacked die configurations of the PMUT and ASIC. Stacked die is achieved via wafer-to-wafer, chip-to-wafer, or chip-to-chip bonding. These packages can be executed on laminate, lead frame, or molded interconnect substrate, also known as MIS, which can enable package sizes, small package sizes, and also performance advantages, such as signal integrity and also thermals. PMUT packages also leverage flip chip packaging, where basically the PMUT or ASIC dies can be bumped using plated solder bump, gold bump, and copper pillar technology. The advantages of flip chip for a PMUT package is smaller XY dimensions, Z height, and support of high-speed signals. Shown to the right are 2 hybrid flip chip plus wired bonding configurations, illustrating how a PMUT die could be stacked onto an ASIC that has been bumped and flip chipped onto a substrate, followed by the wired bonding of the PMUT to either the ASIC and or the substrate. The rightmost illustration shows how a through silicon via PMUT die might be flip chipped onto an ASIC, which is then die attached to the substrate for subsequent wire bonding. There are so many options available that are cost driven, PMUT ASIC design driven, supply chain driven. It is important to consult a packaging expert before silicon design lock. Turning to MEMS and sensor cavity packaging technology, PMUT devices have a wide variety of applications, and then a wide variety of package technologies are required. Taking film-assisted molding, for example. At Carson, we've developed our FAM expertise via our development of complex MEMS pressure sensor packages for automotive applications. In the next slide, I'll show you how we're leveraging FAM technology. But before I do, I'd like to mention some of the key considerations related to PMUT device assembly and design. The first being that one must remember that PMUT membranes are thin and fragile. Therefore, precautions must be taken to avoid damage during wafer fab, probe, handling, and packaging. Second, defining the optimal interface media, either incorporating a matching layer or presenting an exposed PMUT array to the environment. Third, defining what will be the most efficient package design to achieve cost, size, and performance. Now, I would like to show you PMUT package architectures that are now being developed. The first two configurations here at the bottom were conceptualized between SilTerra and Carson. Looking at the first row, this is a wire bonded PMUT die that has been film assisted molded to create an open window, exposing the PMUT array, yet protecting the wires and any components that have been overmolded. The end application here is for haptics, gesture recognition. This may seem like a simple package, but there are tooling design rule considerations, tolerances, and assembly process parameter complexities. Looking at the second row, again, we have nearly the same package configuration, except in this case, there's a matching layer of PDMS, a form of silicone, with the cover glass, the end applications being biometric fingerprint sensing. To end with a few market examples for PMUT packages, shown in the top row is a PMUT that is covered by a lid or ported, referring to a hole in the substrate. This is a PMUT device for an application such as proximity sensing. The substrate has a porthole that allows acoustic energy to be transmitted and the reflected waves to be received. In this case, by no means are the packaging options exhausted. At Carson, we continuously monitor MEMS and sensor packaging advancements to ensure that our roadmaps are aligned to support new MEMS device market adoption. For instance, the last package configuration that is shown is an example of the advancements in PMUT packaging, such as PMUT-based photoacoustic imaging module, which represents the level of integration and cross-disciplinary design, MEMS, optics, and photonics. That is demanded of advanced packaging professionals and packaging service providers. The industry will only continue to see more of this SIP design and technology integration. That is my brief intro into advanced packaging for PMUT devices. If you have a PMUT device that you're conceptualizing, consult with an advanced packaging professional. Again, my door is open to you, and I'll be glad to hear from you. My phone number and also my email are here on this slide. Thank you.
All right, John, thank you very much. Excellent presentation, and thank you for sharing your contact information. Very good. You guys have so much experience with packaging. We encourage everybody to take this opportunity and get in touch with John, for your current project or future project. John has been in the industry for many years and is a great contact and a great guy. So, John, this is great. Let's take a few questions. And we have the majority of people, big crowd still with us. And, as speakers, you guys are doing a great job, but I'm honestly very, very impressed with the audience and how much participation we've gotten. And a lot of people, majority of people are still online. So thank you. Okay, let's do a few questions. So are TSVs being used currently in production? Hear so much about it, but yet there seems to be elusive proof of this. So John, any comments on TSVs?
For the sake of time, I really couldn't show a lot of the wafer level packaging, but TSVs are being used, and they're being used in stacked die configurations. And so this is an area where you really want to talk to your wafer fab and your provider there, and to understand what they're offering in terms of TSVs and stacking these PMUTs onto ASICs. So yes, I want to just say an apology. We can't cover everything in 7 minutes, but wafer level packaging and found out wafer level packaging is being used extensively here in PMUT packages. So yes.
All right, very good. Please follow up with John to discuss more. Another question from Greg Frey is the previous question. What are the typical encapsulants used to protect PMUTs? While not damping the membranes. So,
well, we're more familiar with the PDMS, the polydimethyl siloxanes. That's the extent of our experience. But when it comes to the molding compounds, we also have experience with that. But I think we have the most experience with PDMS. But we'd be happy to look at how we can dispense more materials and build prototypes. And then do the simulations and testing. There's been a lot of talks today about simulation. So in selecting these materials, it's important to know the material properties, model them, and then go off and build them under a proper DOE.
All right, very good. Let's take a few more. Do you have a solution for PMUT arrays for medical imaging applications?
Today, we're basically would be working with, that answer would be no, primarily. We're working today in the automotive space. We're IATF 16949 certified, but doesn't mean we wouldn't want to. It's just a matter of sitting down with whoever asked the question. I have certainly reached out to medical companies that are working with PMUT to try to understand packaging needs. So that is not an answer coming from me. It's just that we want to be able to work more in that area. And I made it a significant portion of my work in the PMUT area to reach out to people like yourself.
Yeah, again, as I was mentioning in my opening remarks, PMUTs for medical imaging is still an emerging area. And so It's a good time to contact John and discuss more. So good question. Thank you, Mark.
Chances are, if you're doing medical, I've already reached out to you guys. And so it's just a matter of the right timing and now having this type of talk where the door's open to you and another open door.
All right, excellent. Let's do a couple more. Question from Marco Ferreira. How do you guarantee the process control?
Well, within process, that's a good question. So within Carson process control, for us, we have quality systems in place. Here at Carson, we're Industry 4.0, everything is robotized. We have the ability to take all the data off of every machine. Every one of our machines has cameras for quality control. We also have QC. So we'll take components off the line and we'll measure and monitor all dimensions. One of the things that I think is interesting too is around PMUT, right? We also want part of that QC could be having offline testing to ensure that PMUT devices stay within a certain band of performance, right? So this is, and also testing. So one of the major issues with PMUT is that not every OSAT, outsource assembly and test company, is going to have an ability to test quality for these devices. So if there are solutions that you have at your company like Carson can take these tests and get them ready for high volume production. So there's quality all along the path from design to the building of prototypes and also the monitoring and production.
All right, great. Let's do one more, and then we'll conclude, and then I'll just make 1 or 2 minute remarks, and then we'll be all set. So, John, last question: What is the assembling what is the assembling percentage for wire bonding versus flip chip technology? What do you guys see?
Well, in general, in the marketplace, right, it's generally around 60-40 or 70-30, depending on the market. Mm-hmm. I think still in automotive, it's 70-30. With PMUT, it just depends. We talked about in your slide, from Yo, they're showing that a majority of these packages are going into automotive, right? So in automotive, they're using a lot of wire bonding, right? So I'd say maybe that's just a guess. We have to look at the data. I think that Yo presented today, and but the majority, like I said, in automotive is 70-30.
Okay.
70 being the wire bonding. Yeah.
So more like 60 to 70 wire bonding and 30 to 40 would be flip chip, right? Okay, great. Yeah, John, this is great. We have more questions coming in. We'll be sharing the questions with each speaker, corresponding speaker. Of course, John is sharing his email address here, so please feel free to grab that now and then just contact John directly. John, again, great talk, very nice Q&A, and the audience also a great job with the Q&A. John, thanks again.
No problem. Please contact me anytime. My phone number is right there. Thank you so much.
Very good. Thank you very much. All right. So now John will stop sharing, and I'll bring up just one slide very quick here. So, and then we're almost done. So we appreciate everybody sticking around. So again, I just want to say, I remind everybody that we will be sending out early next week a link with all of the slides, a download link with all of the slides. And also in the same email, there will be a link or some way to access the recording of the webinar. So we'll be sending both of those early next week. So, you know, again, Monday or Tuesday next week, please look out for that. If you do not see it, please feel free to email Jessica. Here are our contact emails. So jessica@microtechventures.com or myself or both of us, Mike at microtechventures.com and Jessica at microtechventures.com. And about anything related to the webinar, or if early next week, again, if you don't see that email, just let us know. We'll get that information to you. Wanted to thank the audience again. We had around 280, actually more than 280 participants. We had a great participation on this webinar. We went a little longer than we expected. We thought it would be about an hour and a half. We went slightly longer than that. But the Q&A has been great, as I think everybody could tell. We couldn't even get to all the questions. People stuck around. Majority of people actually stuck around all the way through the end. We really appreciate you guys. And the speakers did a great job. All the angles, or most of the key angles, were covered. Certainly for an hour and a half length, we thought that the speakers did a great job and provided a lot of very good information. So we thank everybody again. We thank the speakers for preparing your talks and delivering your talks, and we thank the audience for your valuable time to participate in today's webinar and also to be engaging and ask all the great questions. So we look forward to seeing you guys online and in person, hopefully increasingly more in person in the coming months and certainly into next year. We also look forward to seeing you at our conferences. I made a few announcements in the beginning. You can check out our website, microtechventures.com, to see about our upcoming conferences this year and into next year as well. So I think this brings us to the conclusion of today's webinar. Again, great job, everybody. I'll ask Jazz to, as soon as I stop sharing, to bring up just that webinar slide, and also to play music for a few minutes as we conclude. Thanks again, everybody. Have a great summer. Stay healthy, stay safe, and best wishes to all of you and all of your families and all of your loved ones. We appreciate it. Thanks again. Take care. Bye-bye.